Alright, chemistry, this is your video lecture for chapter 6, talking about section 3, Ionic Bonding and Ionic Compounds. Now, realize we're going to be using the term ionic compounds because if we say molecular compounds or molecules, we're assuming covalent bonding. But we covered that in section 2, and now we're moving on to ionic bonding, so we have to use the term ionic compound. After this video, I want you to be able to compare a chemical formula for a molecular compound with one for an ionic compound. Discuss the arrangements of ions in crystals, define lattice energy and explain its significance. And when I say explain its significance here, I do not mean tell me that it is significant, but tell me what it signifies. And spoiler alert, it's the ionic version of bond energy from covalent bonding. Then I want you to list and compare the distinctive properties of ionic and molecular compounds. And lastly, write the Lewis structure for a polyatomic ion given the identity of the atoms combined and other appropriate information. So let's get started. Most of the rocks and minerals that make up Earth's crust consist of positive and negative ions held together by ionic bonding. For example, table salt, you guys know this, made up of Na and Cl, consists of one sodium and one chloride ion combined in a 1-to-1 ratio, Na plus and Cl minus, such that each positive charge is balanced by a negative charge. An ionic compound is composed of positive and negative ions that are combined so that the numbers of positive and negative charges are equal. Now that fact is going to be foundational for this chapter, next chapter, and all the following chapters, because we have to remember that when constructing the formula for an ionic compound, the overall charge must be neutral because there are equal numbers of positive and negative charges. Now, most ionic compounds exist as crystalline solids. A crystal, that word crystal in there, a crystal of any ionic compound is a three-dimensional network of positive and negative ions mutually attracted to each other. Now remember, for a covalent bond, it's one atom bonded to another atom to create that covalent bond. Just two atoms involved. In contrast, an ionic compound is not one ion attracted to one other ion. It's going to be several ions attracted in this multi-directional, three-dimensional network, right? And that is in contrast to the molecular compounds, right? Molecular compounds are a completely different setup. Now, they're both trying to accomplish the same thing, that lower energy configuration, which is, we have a name for it, is a noble gas electron configuration, or satisfying the octet rule. There's just different strategies for accomplishing that. So the chemical formula for an ionic compound does not represent molecules, right? So when we have that NaCl crystal, it's not one Na and it's not one Cl. In fact, it's millions of them. It's millions of them. So if NaCl doesn't represent one molecule, what does it represent? It represents the simplest ratio of that compound's ions. Now, we know that NaCl, those two ions are going to occur at a 1-to-1 ratio because that is the ratio at which there are equal numbers of positives and negative charges and having a neutral or zero overall charge. So we give that formula, that NaCl, a special name. It is the formula unit. A formula unit is the simplest collection of atoms from which a compound's formula can be established, NaCl. So to draw this contrast a little bit further, we have covalent bonding, which we covered last section. It is atom C and atom D sharing a pair of electrons, and so we have atom C and atom D. But when we represent ionic bonding between ion A and ion B, the electrons are being transferred to create these ions here, or should I say these are starting as atoms, neutral atoms, and then they're ionizing, that transfer of electrons. And we create this three-dimensional, multi-directional network, right? Not just one Na and one Cl, but a whole bunch of them arranged in this kind of ordered pattern in 3 dimensions. We have X, Y, and Z. Now we have a typo here, but I fixed this on your notes. The sodium atom, right, the neutral sodium atom, has only one valence electron. That's a typo. It's 1. I don't believe it's correct on your notes. Has 1 valence electron, and the chlorine atom, the neutral chlorine atom, has 7 valence electrons. Atoms of sodium and other alkali metals will easily, violently lose that 1 electron to form cations, aka positive ions. Now, atoms of chlorine and the other halogens will easily gain 1 electron, or violently gain 1 electron, to form anions, or positively charged, goodness. Anions are negatively charged ions.
We have previously learned about the formation of ions. Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses 1 electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide? Please pause the lesson and resume when you are done.
Do it.
Magnesium transfers its 2 valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine. Calcium loses 2 electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming 2 chloride ions. The calcium ion is electrostatically attracted to the 2 chloride ions because the opposite charges must fully balance each other out. In all 3 examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
In an ionic crystal, ions, right, after that formula unit has formed, in an ionic crystal, ions will minimize their potential energy, and we just saw examples of calcium and chloride, sodium and chloride, magnesium and oxide. Those ions will minimize their potential energy by combining in an orderly arrangement known as a crystal lattice. Within this crystal lattice, there are attractive forces existing between oppositely charged ions within that lattice. But at the same time, there are repulsive forces existing between like-charged ions within the lattice. The combined attractive and repulsive forces, right, that pushing and pulling at the same time within the crystal lattice will determine the distance between ions and the patterns of the ions arrangement within the crystal.
Bonding in a crystal lattice is controlled by the size of the ions involved and the stability of the final structure with respect to positive and negative charge. The attraction among ions occurs in all directions. In sodium chloride, there is 1 sodium ion for every chloride ion. Chloride ions attract as many sodium ions as possible. Similarly, sodium ions attract as many chloride ions as possible. In this way, the charge on each ion is balanced as evenly as possible by the surrounding charges on its neighbors. The ions pack together, producing a regular, infinitely repeatable structure called a crystal lattice.
And so there are different types of crystal lattices. We have the NaCl lattice, right? Alternating sodium and chloride ions. And you can see how each ion is surrounded by multiple ions of opposite charge. Even when we go for a different formula unit, here we have cesium and chloride. We still have a particular ion surrounded by ions of opposite charge. Now, there might be a slightly different ratio of surrounding ions, right, to create a slightly different shape, where with sodium chloride, one sodium ion is surrounded typically by 6 chloride ions. Over here, cesium is so much larger as an atom that it actually has enough space surrounding it to surround itself with 8 chloride ions, but it's still going to be a regular repeating structure. The distance between ions being determined by the lowest potential energy possible.
For these sodium and chlorine ions, a lattice structure is more stable than a gaseous cloud. Energy is released as they come together to form a crystal lattice structure. 787.5 kilojoules of energy are released when the sodium cations combine with the chlorine anions to form solid crystalline sodium chloride. This energy is the lattice energy.
And so this is the ionic version of what we learned about in section 2 with covalent bonding, called bond energy, which was the amount of energy required to break a bond. So the lattice energy is the same concept. It's the measure of the strength of a particular ionic bond. The big difference here, not only are we talking about ionic bonds in a crystalline solid, we're also referring to 1 mole of that particular substance, whereas with a bond energy, we're referring to one individual bond, right? So a lattice energy is per mole. So now we have to compare the properties of ionic and molecular compounds. So the force that holds ions together in an ionic compound is a very strong electrostatic attraction because they're whole charges. In contrast, the forces of attraction between molecules in a covalent compound are much weaker. And that makes sense because in an ionic compound, we have whole charges attracting one another, and that's quite a bit of electrostatic attraction. And if you're thinking in a covalent bond, there's still a whole charge and an electron being attracted by many whole charges in the nucleus of the bonded atom. You're right, but remember that there is a whole bunch of electron shielding going on, so that mitigates that overall electrostatic attraction. And functionally, it makes a covalent bond much weaker. This difference in the strength of attraction between the basic units of molecular and ionic compounds gives rise to the different properties that we see between the two types of compounds. Molecular compounds have relatively weak forces between individual molecules, and so they don't hold together in rigid structures. Therefore, they melt at fairly low temperatures. In contrast, the strong attraction between ions and an ionic compound gives ionic compounds some of their characteristic properties, like a very high melting point. They are hard but brittle, meaning once you apply a minimum amount of energy, with like hitting it with a hammer, they will shatter, right? They're hard, but at a particular point, they will shatter very, very easily. And also, they are not electrical conductors when they are in the solid state because no ions can move. But if you do manage to melt them, they will conduct electricity because obviously those ions can move. And so let's take a look at these melting and boiling points. And we're going to see the difference between ionic compounds, the first 3, and covalently bonded compounds, the next 5 there. We see the huge difference in melting point and boiling point here. So your typical ionic compound, we're in the high hundreds of degrees Celsius in order to transition from the solid state into the liquid state. right? And so we're talking about the type of temperature it takes to melt lead here. When we're getting up into the high 700s, 800s, 900s, especially for that magnesium fluoride we see up there, over 1,000, actually over 1,200 degrees Celsius. These are incredibly high temperatures that we do not see here very often, if at all, here on Earth. And so we are going to see those ionic compounds as solids. They are often solids, pretty much all the time solids. Whereas these covalent compounds, you can see that their melting points are actually very, very low. A lot of them are actually in the negative degrees. And so we are going to see them either in the liquid state or in the gaseous state. We go over here and we see that room temperature is the point at which a lot of these will boil and become gas. So if you're ever doing some sort of like dichotomous key and you're trying to identify whether or not a particular unknown compound, a particular sample is ionic or not, we're going to examine the substance. Now, all ionic compounds are solid at room temperature. Like we saw, those incredibly high melting points are not going to be satisfied at room temperature, so they'll be solids. Now, if that substance is a liquid or a gas, then it's clearly not an ionic compound. However, if it's solid, it doesn't mean it's automatically an ionic compound. It could still be covalent. What we'll do is we'll tap that substance gently, right, with a hammer or something, nice and soft. We don't have to bang it. An ionic compound is going to be very, very hard. So if it's an ionic compound, it should not break apart easily. You're going to have to put a decent swing into breaking that thing apart. And even if it does break apart, it's going to fracture into smaller crystals, as opposed to crumbling into a powder, which covalently bonded substances like let's say just like a sample of sulfur, for example, just all nonmetal sulfur, it's just going to crumble into a powder as opposed to breaking into more and smaller crystals. We can also heat the substance. Ionic compounds generally have very, very high melting points and boiling points, and so if we identify that whatever that substance is melting at a kind of a lower room temperature, like 70 degrees Celsius to 100 degrees Celsius, that's definitely not ionic. Definitely not ionic. We saw on that table that ionic compounds have melting and boiling points much, 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 much higher than that. So if the substance does melt, if we manage to melt it, we can test its conductivity to determine if the melted substance conducts electric current. An ionic compound is going to be a good conductor of electric current when it's in the liquid state, because those charged species, those ions, they can move when they're in the liquid state. We can also dissolve whatever the sample is into water. And again, we can test its conductivity because ionic compounds are actually very, very good electric conductors when they are dissolved in water. Now, that doesn't mean that they've become liquid, right? Being in the liquid state is different than being dissolved in water, right? So ionic compounds do not conduct electricity in the solid state, but they will conduct electricity when they're dissolved in water. So moving on to polyatomic ions, and the name is exactly what it sounds like. There are certain atoms bonded covalently to each other to form a group that has both molecular and ionic characteristics. Now, a charged group, it's charged, right? So there's the ionic characteristic. There's an excess or deficiency of electrons, right, to create a charge. So that's an ionic characteristic. But they're covalently bonded together. No single atom within the group is an ion, right? So they're covalently bonded atoms. So that means that you're going to see that these are all nonmetals bonded together. But if we do have a charged group of covalently bonded atoms, we're going to call that a polyatomic ion. Now, like other ions, polyatomic ions have a charge that results from either a shortage or excess of electrons. An example of a polyatomic ion is the ammonium ion, which is NH4 with a +1 charge. It is sometimes written with brackets to show that it is a group of atoms as a whole that has the charge of the +1, and not mistaken for simply one of those hydrogens having a +1 charge. So the charge of the ammonium is determined as follows. So we know that nitrogen has 7 protons because it's, number 7, And there are 4 protons from the 4 hydrogen atoms. So as a whole, altogether, that's 11 positive charges, right? But when we count the number of electrons, right, when nitrogen and hydrogen atoms combine to form an ammonium ion, one of their electrons is lost. And that gives the polyatomic ion a total negative charge of -10. And so if we add those numbers together, the +11, the -10, we have an overall charge of +1, and that's where the +1 comes from. So here's some examples of Lewis structures of very common polyatomic ions. Please copy these down. Make sure that you're familiar with these, because these are going to be used throughout the rest of the course, especially if you decide to take a gander at AP. We're going to be using these polyatomic ions very, very regularly.
Comparing monatomic, diatomic, and polyatomic structures. A molecule or ion that contains only one atom is monatomic. The prefix mono means one. A molecule or ion that contains only 2 atoms is diatomic. The prefix di means 2. A molecule or ion that contains more than 2 atoms is polyatomic. The prefix poly means many.
All right, chemistry, that will do it for section 3 of chapter 6. I will see you next period.